All right. The online people, can you hear me? They're now responding. We'll start in just 1 second. Can anyone hear me? I hope they can. All right, so while we're waiting for it, well, you see I have this GIF over here, right? Like showing you how we access the main memory through the cache, right? So cache is usually part of the processor, and it's gonna send the address request. If there's a cache miss and it's falling through all the cache levels, it's gonna send a address request to the main RAM, and then the data will come back from the memory, going back to the cache, and then finally coming back to the main CPU, right, to the ALU processing units. And then the other diagram, this is the core of a first generation Intel i7. So let me move the controller over there. So this is a first generation Intel Core i7, the inside structure. You see, this is what you buy, right? The main processor. And then if you remove the lid, then you'll see the bare die. And this die, the rectangular shape, is represented by that diagram. So in the die, you see this is a 4-core processor. And we have a pretty big region dedicated to the L3 cache, right? So that probably tells you how important the cache is. This is roughly almost like 1/4 of the size of the processor, right? You're spending that much resource just for the cache. And cache is therefore very important. And by the way, so I just showed you the L3 cache. Maybe I'll do it over here with a pointer so that the online people can see me. Can you see the mouse? Yes. So this is the L3 cache. And inside each core, we also have L2 and L1 cache, right? This region over here, the regular corner, the regular looking corner, this is actually the L2 cache. And the L1 cache is also a quite regular pattern, sitting a little bit closer to the center of the core. And at this level, right, the distance matters, whether it's like 1 millimeter away from the core or like 5 millimeter away or 1 inch away, they do make an impact on latency. And that's the reason why L1, which is sitting just next to the core, around the center of the core, L2 at the corner of the core, and L3, it's allocated so that it's pretty much adjacent to any of the cores, right? So the layout also, it's laid out considering the cache latency. All right. And speaking of cache placement, we have this formula C equals ABS, right? Associativity, block size, and number of sets. And in this example, we have 4 sets. Well, this is a way I like to illustrate the cache, especially for solving questions, right? Rather than keeping everything like tag, data, valid, and dirty bits, I just draw a simple grid. And each row of the grid represents 1 set. And that's going to be, indexed by the index bits. And the columns represent the way associativity, right? In this case, I have 4 sets, so I need 2 bits to index it. I have 8-way associativity, so I have 8 columns over there. And suppose the block size is 64 bytes. This is a pretty common block size that we see, throughout the lecture and also in many homework questions. Based on these parameters, then I can plug them into the ABS formula, right? 8-way times 64-byte block size times 4 sets. That gives me a 2 kilobyte cache, right? And of course, there are a number of different placement policies for cache. You could make it a 4-way set associative cache of the same size by increasing the number of sets but reducing the weight associativity. You could also, make it like very narrow but very tall, and this is a direct mapped cache, right? Like there's no associativity at all, or it's like a 1-way associativity. So whenever you index into a set, there's only 1 element, and there's no need to search through, different ways. So this is very fast, but also conflict becomes an issue, right? There's no way that you can accommodate 2 conflicting memory accesses. If you just turn that tower all the way down, then you have a very long, but again, very narrow set cache placement. Over here, you just have one set, but the associativity is very high, right? All of the blocks are set associative. And this is what we call the fully associative cache. And what I'm showing here, these caches all have the same size, right? The total size is the same, but different placement will lead to very different behaviors, right? In terms of latency, hit rate, miss rate, those kind of things, right? But you see, I still have a space at the bottom, so I'm not done yet. You can also have a different block size, right? You don't have to stick with 64-byte block. You could have a 128-byte block and fewer blocks. And this is also a fully associative cache. Actually, you can use the 128-byte block size for any kind of cache placement, right? You can use it with associative cache, direct connect cache, or fully associative cache. All right, any questions so far, right? A basic review of C equals ABS. All right, so now it comes to the first practice, right? You have seen this quite a few times in lecture. So maybe I'll give you the cache placement over here, right? 4-way set associative cache, 8 sets, 4 ways, 65-byte block size, right? And the basic question is for you to figure out how many bits do I need for each field, right? So let's define around the annotation. Now I should be able to draw on the iPad, right? So because the block size is 64, how many bits do we need for the block offset? Someone? 6, nice. So 6, right? Log 2 to the block size, right? What about set index? I'm trying to index into one of the sets. So we have 8 sets over here, and we need to index into one of them. So we need 3 bits. That's right. Right. Essentially, we're going to use set index to select one of the rows, right? So log 2 to number of rows, in this case, number of sets, will be the number of bits for set index. And finally, all the remaining bits will go to the tag. So 6 and 3 and 64 minus 3 minus 6, which is 50. Well, why is my math so bad? 55. Yeah, 55 bits for the tag. All right. And now let's also look at a particular address that I want to read or write, right? So suppose the array A, this is a double array of doubles, starting at address, in hexadecimal 40000. And then the question is, what about A3? What is the address for A3? Right? I'm putting down the address for A0, the starting point of A array in binary over there. And then what is my A0? Sorry, what is my A3's address? Right? In binary, how do I represent it? Do I just put 2 zeros, 2 ones at the end, right? On the rightmost positions? Or do I? So they're saying 1 over here and 1 over here, right? That's correct. And why is that, right? Remember, this is a byte addressable cache from memory, right? And the distance between A0 and A1 will be a double number, which is 8 bytes, right? 64-bit double number is 8 bytes, right? So A1 will have a 1 just over here, and A3 therefore will have a 1 over there and also a 1 on the next position, right? And well, this is how you just write down the binary address of a particular element. But then we also want to divide it or regroup these bits according to my field, right? So for example, I know I have 6 bits of block offset. So those 6 bits belong to one group. And I can essentially ignore those bits when analyzing the cache behavior, right? We're going to use them eventually when we find the right block from the cache, and then we pick one double word from that block. But when it comes to accessing the cache or analyzing the hit-miss behavior, we don't need to worry about the block offset. And then we have 3 bits for set index. So that's 000. And therefore, we know that this block will go to the first row of the cache, right? Index 0. And effectively, what will happen is, I'm going to take the whole block from A0 to A7, right? That is 8 double numbers in one block and put them inside 0. Yes, questions? Give me 1 second. All right. Go ahead.
I was wondering if you could, I guess, show us how, I guess you did that quick translation to, because we have to add 24 bytes, right? To 24 bytes.
That's right. Okay. So to get A3, right? One way is to think, A0 and A3, they differ by 3 doubles, right? 3 doubles is 3 times 8 bytes, which is 24 in binary, right? 24 is 16, sorry, annotation equals 16 plus 8, right? So in terms of binary number, this is position weight 1, 2, 4, 8, 16, right? So I'm going to put 2 ones at position 16 and position 8, right? Those are the positional weights for each binary position. That's one way of doing it. But the other way, the way I like to do it is to first ignore the last 3 zeros, because I know I'm dealing with a bunch of doubles. And for any double number, their address will end with 000, right? I'm always addressing the beginning of a double word, a double number, right? So the rightmost 3 bits will always be 000 for doubles. And therefore, if I look at the remaining bits, and then 3 is just 3, right? 1, 1 at the rightmost positions. But effectively, I'm doing the same thing, like whether you take into account the 8 bytes at the beginning or at the end, right? They will produce the same result. All right. So moving on to the next example. Well, somehow I couldn't erase the writing. The writing is embedded in the screen share. So let me redo it. All right. So now the real practice, right? I give you this code, right? Very simple code. I'm just going through, every other element in the array, right? A0, A2, A4, A6, A8, etc. Right? And the question is, for that cache placement, right? For we set associative cache with block size of 64, what is the miss rate? Right? So let's spend maybe half a minute just thinking about this question. Right? The question is, what is the miss rate for this code? Anyone want to just, throw in a guess? Yeah.
50%?
50%. Okay. So do we have any other competitors, right? Anyone has the same or different answer? Right, so maybe let me put down in the meantime, I'll put down the access pattern, right? A0, A2, A4, A6, A8, right? A10, etc. I think that's enough for our analysis. All right. Anyone has what's your answer? 1 in 4, 25%. All right. So maybe let's just go through this access sequence, right? A0, the first time I'm reading anything, right? It must be a compulsory miss. So this is a miss. What about A2? Well, in the meantime, right, when I'm accessing A0 and I realize it's a miss, I'm gonna fetch the block from the subsequent memory hierarchy levels, whether it's L2, L3, or main memory, right? And what I will bring to the cache will be the whole block containing A0 to 7. Right, you agree with me? 64 byte block that can hold 8 double numbers. So anything from index 0 to 7 will be placed in the cache. And then A2, well, it falls in that range, right? 2 is between 0 and 7, so this is a hit. 4, also in the same block, this is a hit. 6 in the same block is a hit. And then when it comes to A8, that is actually the beginning of the next block, right? So we have a compulsory miss again. And then 10, and in the meantime, I'll bring the block of between A8 and A15 to the cache. Right, and I think they will probably go over here. You see, A8 has index 001, right? So I'm gonna put that in the second set, A8 to 15. Right, I'll bring it to the cache, and then 10, 12, 14 will all be hits, and then 16 is another miss, right? So 1/4, that is my miss rate. Yes. 1 second. Microphone online.
Why goes to next row, not next column?
Because when you look at the address for A8, right? I'm putting the binary address over here. These 3 bits in the middle, the right one, the right bits, that is the set index. Right? So when that's 001, I'm only gonna look into the the set with index 001. That is, the first row that's index 0, the second row is index 1, 2, 3, etc. Right? I'm using the index bits to select one row or one set to put my block or to read my block. All right. All right. Yes.
One more question. Isn't there also potentially one compulsory miss for a result?
I'm assuming, well, right now I assume that result is not in the memory, maybe a register.
I see.
Right, but maybe, if result comes from the memory and eventually needs to go to the memory, then there will be, one miss at the very beginning to read it, and then it will be stored in the register, and then I will just keep it in the register until eventually I need to put it back into the memory. Right, but oftentimes, if you're seeing these kind of intermediate variables, these are often just stored in the register, right? They do not go to the memory. Right. All right, and then I'm making a small tweak, right? I'm reversing the traversal order. These 2 codes will do the same thing, right? One is going from 0 to 799, the other is from 799 back to 0, right? So functionally, these 2 codes will be equivalent. But what about the miss rate for the new code, the code B? Yes.
Really don't. Isn't it 100% miss rate? Because we always load like the next reference.
That's a good guess, 100%. Right? Anyone has a different opinion? And for the online people, feel free to put your answer in the chat or just, unmute yourself and speak up. I think I have my speaker turned on. Right. Everyone agrees with 100%?
Or does it load in the other direction? I don't know.
Yeah, the question is, does it load in the other direction, right? Well, the thing is, right, think about this. Every time when we do a load, we're loading a whole block. But, the block we don't have to load at the beginning of the block, right? Even if we're trying to access an element in the middle of the block or at the end of a block, we will still just bring that whole block into the cache, right? So, well, for code B, eventually I'm going to access like A6, A4, A2, and A0. Of course, I'll start with all those big numbers, and eventually I'll get here. But, I'm just going to show the pattern here. When we are at address A6, right, it's a miss. It's the first time I'm seeing that block, 0 to 7 block, right? So I need to bring that whole block into the cache, right? So again, at that point, the cache is probably already full, but I will just throw away a cell, set 0, and then put my A0 to 7, that whole block, into the cache. And therefore, all the subsequent accesses, right, 4 to 0, those will all be cache hits, right? Again, the pattern over here is like 1 miss followed by 3 hits. So we have the same miss rate, whether it's code A or code B, right? The point of this example is just to remind you that, even if you're accessing the last element in your block, you're still bringing the whole block. And you can benefit some of the, the address is a little bit earlier than the one you first accessed. Yes.
So if we are
Microphone. Yeah.
So if we are accessing the last element, like from 0 to 7, we will still be bringing the whole block from 0 to 7. If we're accessing
Yes.
A7.
Yeah. So if you're accessing A7, yes, you will bring the whole block 0 to 7 into the cache.
And if we're doing A6, it's still 0
It's
to
the same, right? It's
Oh.
the same whether you're unloading A0 or A7 or anything in between, because they have the same index and tag. They only differ on the block offset. And as I mentioned at the beginning, the block offset doesn't matter when it comes to analyzing, the cache hit or miss behavior. All right. So erase, and let's move on to the real practice. This is from the assignment, and it took me a while to just go through the access pattern. I think it took me a good 2, 3, if not 4 hours for the assignment. But rather than going through this exact example, I figured that I should probably use some different numbers so that I can show you the exact details along the process, right? If I can't just show you the solution, but if I change the numbers, right, keeping the same code, but changing the numbers to what I presented over there, right? I'll show you the whole process of analyzing the cache behavior using this matrix or grid that I drew earlier, right? And this example, based on my number, you see this is a much smaller cache, right? And much simpler patterns because we only have, n equals 16 rather than 128, right? So, it's a little bit more manageable. But at the same time, eventually the access pattern is pretty complex in this example. So I figure this is probably 18.75% harder than your real homework assignment. And therefore, if you can handle this question, you can solve the homework. All right. Again, I'm just keeping my grid over here. This is different from the homework. This is based on my numbers, right? We have 2 kilobyte cache, 2-way 128-byte block, right? Pretty big block, a 2-way associativity, and not many sets, right? This is a small cache. And if you use the ABS formula, you have 8 sets, right? And I'm illustrating this 2-way 8 sets cache over there, right? For those of you who haven't looked into the homework before, maybe let's spend a little bit of time just looking through the code, right? This code is, we have 2 double arrays, and then we're trying to access, well, for B, the pattern is pretty simple, right? We're accessing B0, B1, B2, B3, and all the way to B127 times 127, right, sequentially. For A, it's a little bit more jumpy, right? We start from A0, but then in the next iteration of the inner loop, we're gonna go to A16, and then A32, at 48, and 64, and so on. All right. So this is what I'm saying. So for that code and my parameters, I'm accessing A0, reading from A0, writing to B0, and then reading from the second iteration of the inner loop, reading from A16, writing to B1. Third iteration of the inner loop, reading from 32, write to B2. All right, and these are the binary addresses. Well, the thing with this question is that at the beginning, you do need to write down these binary numbers. But after a little while, you will start to see the behavioral pattern based on my grid or my table over there. And at that point, you don't have to look that carefully into the binary numbers anymore. Right? We're trying to find the pattern. And once we found the pattern, we know that this pattern is just going to repeat throughout the loop, right? Throughout all the iterations. But at the beginning, to find that pattern, we need to look into the binary numbers. All right. So first, A0. Actually, well, I do have the solution on the next slide, but I want to guide you through the process. So I'll create a presentation mode and just use some ad hoc pointers to draw your attention. And we're going to walk through this example together. All right. So first, A0, right? I mainly look at the index and set. The index and tag. So first, index 000, it's a miss, right? I don't have anything in the cache, so it's definitely a miss. And knowing that index is 000, I'll put my block over here. And what do I have in that block? Right, I have a bunch of double numbers, but what is the index range? 0 to 15. Right, different from the previous example. Here I'm dealing with 128 byte blocks, right? And double is 8 bytes, so I have 16 double numbers in one block. So anything from index 0 to 15 will go into the first row of the cache. And by the way, this is a two-way set associative cache, so the order of the two columns doesn't matter, right? We just need to remember which one is least recently used when it comes to replacing a cell. All right, and then move on to the next one, B0. Well, it has the same index, 0, 0, 0. What the cache will do is it's gonna search through all the cells or all the blocks at the index 0 and see if the block is already there or not. And B0, of course, doesn't match A0, and there's nothing here, so it's a miss, right? This is also a compulsory miss. The first time I'm seeing anything from B, and they are not replacing anything. Right? And because it's a compulsory miss, I need to bring the whole block into the cache, right? Again, at index 0. So I have B0 to 15 loaded at index 0. All right. And then I'm going to continue to A16. And this time, the index is 001. So I want to look at index 001. And there's nothing there, right? So this is also a compulsory miss. It doesn't replace anything, but I do need to put the whole block from 16 to 31 into the cache, right? And then we're going to accelerate a little bit. B1, index 000, and look it up. I do find a matching tag, right? So whenever I have the B0 to 15 and I'm looking for B2, I know that the tag is going to match, right? But rather than showing the tag in binary, the way I just represent them in terms of index helps you just navigate in the table. All right, so this is a cache hit, and it doesn't replace anything. And the next one, A32, index 010. Well, that's the first time I'm seeing that index, right? So A32 to 47 will come over here, and this is a compulsory miss. Doesn't replace anything. B2, all right, I'm going to come back to set 000, and B2 is indeed over there. Right, so this is a hit. And nothing to be replaced. A48, index 011. I don't have anything at index 011. It's a compulsory miss. So 48 to 63. All right, this is a miss. Doesn't replace anything. And then finally, B3 is in the cache, right? So this is a hit. Right. And once you have filled in the first several rows of the table, right? This is only the partial table. Of course, you need to go all the way, to be 15, the first iteration, and then continue in the second iteration of the alternate loop. But at the beginning, right, you start to see a pattern emerging from these hit-miss results, right? Every access to A is a cache miss. The first access to B is a miss, but then, a bunch of subsequent accesses are hits, right? Because they all belong to the same block. So what we get at the end of, suppose I is 0, that's the first iteration of the alternate loop. And then J goes from 0 to 7. That's, the first half of the inner loop execution. By the end of that, this is what I get, right? This is what the cache looks like. I have just, one block for A, is for B0 to B7. Those are all sitting in the same block. And for each of the A accesses, A0, A16, A32, A48, they will go into different rows because they have different indices. All right. So at this point, right, I have analyzed 16 memory accesses, 8 on A, 8 on B, right? And among the 16 accesses, all the accesses to A are misses. For B, there's 1 miss and 7 hits, right? So I'm continue with the execution, right? Now my J has only go from 0 to 7. I need to continue, right? J equals 8 up to 15, right? That will conclude my first iteration of the alternate loop. So we're going to continue with this analysis. All right. So I have this the box over here. And now what I'm looking at on A, well, I'm trying to write it in a more abstract way or in a shortened way. This is A 8 times 16, right? When J equals 8. 8 times n plus I. So that's 8 times 16. Again, index 0, 0, 0. Wow, I do run into some issue, right? This is index 0, 0, 0. So I will search through my set 0 to see if there's a matching tag. And well, that is not this one, it's not this one, so it's not in the cache, right? But my cache at index 0 is already full. I need to evict or just throw away one of the blocks. And which one do I throw away? Well, this is, of course, a miss, right? This is also a compulsory miss. First time I'm seeing that block. But what do I replace? I do need to pick one of the two blocks to replace. All right. Give you like 5 seconds. Do I evict A or do I evict B? A. All right. I guess, if it's a majority vote, it must be correct. And that's true. We're going to throw away the A 0 to 15, right? The reason is because, the previous memory access right before it is B7, right? So the B block is very recently accessed. A0 to 15, well, that was accessed a while ago, right? At the very beginning of this iteration. So that is a little bit older. I'm going to throw that away, right? So I will throw this away and then put in the block starting from 8 times 16, 8 times 16, all the way to what, right? The next 16 elements, right? 8 times 16 plus 15. I'm gonna also abbreviate it a little bit. I'm just gonna write ... But you get the idea, right? Every time a block stores 16 elements, right? 16 double numbers. All right, and move on to B8, right? Again, look at the index 0, 0, 0. Well, it's still within the same block, right? Everything from B0 to B15 are in the same block. So this is a cache hit. And I don't replace anything. And by the way, because I have already identified the pattern on B, I'm just going to replicate that result for all the subsequent B accesses, right? Those are all going to be hits. They sit at set 0. That block is always there. It's very recently accessed. So it's, rarely throw away. And then move on to this A9 to 16, right? Index 001. Well, it's not this one, but I still have an empty entry, right? So nothing to be replaced. But this is a cache miss, compulsory miss. I need to bring it back into the memory. So 9 times 16 and the next 16, 15 elements, right? And same goes for all the subsequent A accesses, right? We're just gonna put them one by one. Almost, it looks like the second column in the table, but the column order doesn't really matter, right? So it's really just putting them in the set. And then we're going to continue 11 times 16, 12 times 16, and so on. All right. And the end result looks like this. This is when I equals 0 and J goes from 0 to 15, right? In other words, the complete first iteration of the loop, of the outer loop, right? When the inner loop has been traversed 16 times, the outer loop has just been executed once. Right, I equals 0, J goes from 0 to 15. And this is the end result. And to summarize what we have found so far, we have 16 accesses to A. Those are all misses, right? It's our first time seeing every block. And these are all compulsory misses. For the 16 accesses to B elements, we have one miss at the very beginning. And then all the subsequent accesses, all the subsequent writes will be cache hits. Right, the block is always sitting right over there. Right, so therefore, among these 32 accesses that happen in the first iteration, I have 17 misses, 15 hits. So can I conclude that my miss rate is this number? Well, it's a little bit stupid for me to ask this question because, if the answer is yes, I wouldn't put it over here. Right? The answer is, of course, no. And that's because, at the beginning of the first iteration of the alternate loop, the cache was empty, right? By this point, the cache is full. So the second time when you execute the alternate loop, when I becomes 1, you might have a different behavior. We have not reached a stable state for the cache behavior, right? We need to evaluate a few more iterations of the alternate loop until things, start to stabilize a little bit, right? At that point, we can truly determine the pattern. All right. So I'm not sure if you're ready to continue with this exercise, but I'm going to continue anyway. Right. So again, just to bring everybody to the same page, at this point, at the end of the first iteration of the alternate loop, what I have is, most of the elements in A except for A 0 to 15. And that is because there's a spot taken up by B 0 to 15, right? It's always sitting there, and there's no way I can put everything into the cache, right? So at the beginning of the next iteration, I equals 1, J equals 0. I'm accessing A1. I'm reading from A1 first, right? Index 0, 0, 0. And then I would realize that, the block is nowhere to be found in the cache, right? Or in other words, it's, well, where is it? Well, it's nowhere to be found in the set at index 0, right? So I need to throw away one of them. Which one do I throw away? I'm going to throw away A, right? Because, the memory access right before it was B15, right? So B is going to stay in the cache. We're going to replace this block. There's a bunch of bugs for the PowerPoint for Mac. And right now I couldn't select the letter A, but it doesn't really matter. I'm going to bring that block back into the cache. All right. So well, where am I? Where am I? Over here, right? So this is a miss, and I'm replacing the A 8 times 16 and the next 16 elements with A 0 to 15, right? The first block of A. I do have a small question, but I don't want to interrupt the flow. I just want to, leave it for you to think about it. Is it what kind of miss is it? Right? So I just throw away the A 8 times 16, that, block, and I bring in a new block. What kind of miss? Conflict miss? Any other answers? There are only 3 types, right? So, we have 6 people in the room. I guess, each of you throw in one answer, then we'll have other possibilities. This is actually a capacity miss. And I don't want to explain why. I do have a slide at the very end just for you to remember, right? My favorite way to prove conflict miss is to prove that it is not a capacity miss. And to prove that something is not a capacity miss, I need to assume that the cache is fully associative and then precisely analyzing the cache behavior over there, right? It took me a while to just wrap my brain around this definition, but this is a very accurate way to prove conflict miss, or, to distinguish whether it's a conflict or capacity miss. We can come back to this later, after the discussion session, I can explain more to you. But for now, I need to continue, right? And then B16, what kind of hit or miss? Well, that block at index 1 is nowhere to be found. So I need to evict one of the blocks, right? And this one is a little bit older. So I will take out that block, replace it with B16 to 31. Right, this is also a miss. This is a compulsory miss. All right, so I will throw away that block and then replace it with the B block. And then continue with A17. Well, actually, it's using the block that I just throw away, right? It's a little bit sad, but that is what our RU does. So I need to bring it back. I need to replace this one with A16 to 31, which contains A17, right? So it's replacing this one. it's a composite. I say I don't know whether it's conflict or capacity. I need to think about it based on that definition. But it's a miss. All right. So maybe I'll just keep the annotation over here. And then B17, wow, finally we're getting some hits, right? This whole block from 16 to 31 is already in the cache. So I know all the subsequent accesses to B will be hit. And finally, I'm more than halfway through in the table, right? Using this a bit of cheating. And then A33, well, that block 32 to 47 is in the cache. So this is a hit. Very nice. And then 49, well, it's part of this block, right? Starting from 48. So this is a hit as well. Right? This is probably what you need to do for the homework assignment. But as I said, my example is 18.75% harder than yours. So I think you'll have an easier job. Yeah, go ahead. Microphone. Thank you.
So I guess I was wondering, I noticed in this example, we needed to really hit the second iteration of the outer loop to really try to see the pattern. And certainly that makes sense to me. In the homework problem, inner loop has 128 iterations.
Yes. Right.
How do we do that?
Yeah, there's
Are we
no
supposed to go to the second iteration of the outer loop?
Well, still, like when n is 128, right? There's no way you can manually analyze even those complete 128 iterations of the inner loop. And what you need to do is to find pattern, right? Like what I'm doing over here for the B, I know there's going to be one hit followed by 1 miss followed by 15 hits, right? And the same kind of principle applies when n equals 128. So I don't need to manually analyze all those 128 inner loop iterations, right? And similarly, there will be another pattern for A. And again, you might need to analyze the first 10, 12, or 16 kinds of iterations of the inner loop. But by that point, you will see the pattern. And you just, like in Excel, you can drag this pointer all the way to the bottom. It'll just help you fill in the remaining cells based on the pattern, right? And then at the beginning of the second iteration of the outer loop, we need to redo it, analyze maybe the first 10, 12 inner loop iterations until we see the pattern. All right. And again, the pattern in the homework is simpler than mine. Okay. All right. So this is what you get at the end of the first half of the second iteration of the outer loop, right? Which means, I'm done with I equals 1, j equals 0 to 7. I'm going to continue with j equals 8 to 15. But I'm going to skip this slide. You can review it afterwards. I already have the result on the next slide, hopefully. Very nice, right? So what I get in the second iteration is for this, in the second iteration of the outer loop, I have 16 reading of A, 16 writes to B, right? And among them, oh, this number is incorrect, actually. Forget about this. The correct number is, for those 16 accesses to A, I have 4 misses, 12 hits. 16 accesses to B, I have 1 miss, 15 hits, right? The B is a little bit easier to understand. We have a compulsory miss at the beginning, and then all the subsequent accesses are hits. For A, well, you could reason about it, but it's, conceptually it's pretty complex. I think easier to just manually work through those binary examples, right? And based on the pattern you found. And eventually what I found is in the first iteration, I have one behavior. In the second iteration, I have a different behavior. And actually the behavior of the second iteration applies to all the subsequent iterations of the outer loop, right? So there's no need for you to manually analyze the third outer loop iterations, the fourth outer loop iterations, and so on. And the reason why I reached that conclusion that iteration 2, 3, 4 will behave identically is because this is the end of iteration 1. You have everything but A0 to 15. This is the end result of iteration 2. You have everything but A16 to 31. Right? You see the pattern starts to converge. And it is the same kind of access pattern, just everything gets shifted a little bit. But you could examine the third iteration, but I just assume that it's the same pattern. It is the same pattern, right? So I'm cheating a little bit here as well. to save myself some work. Right, and putting all of them together, you can count, among the 16 alternate loop iterations, what is the total number of misses, and then divide it by the total number of memory accesses. Right, you get the miss rate. I don't have the result over here. I did the calculation once, but I forgot whether it's like 18% or 20%, somewhere around there, right? Around 20%. All right, we still have 4 minutes, but you remember in the homework, in the assignment 2, we have 2 questions, right? One of them asking about these memory accesses, the other asking about CPI and memory access time considering multiple cache levels. And actually, question 2, like the CPI calculation is a lot easier than the other one, right? So I'm, devoting much of the time to question 1 and a little bit to question 2. CPI. We have a base CPI of 1. That is pretty much the case in everything we have seen, right? If there's no memory access, CPI equals 1, right? Single cycle processor. And considering the memory access, well, there's a very simple formula, right? Professor said there's no formula, but I do have a formula, but this is not an immediate proof formula, right? This is like a general formula. You need to adapt it to different scenarios. Right, and we are actually using this formula in lecture. The kind of these equations, these numbers we have seen in the lecture slides is based on this formula, right? So CPI consists of base CPI and also memory CPI, right? The actual penalty for memory access. So what I want to figure out is what is, how long does it take to access memory? And that depends on how many memory instructions I have, right? If I have 0%, then there's no penalty for memory access. There's no memory access at all. But if there's 20%, I need to figure out, well, for each memory access, how long does it take? And the time it takes is hit time plus miss rate times miss penalty. Hit rate is also called the latency of the cache. Right? Actually, hit time is a little bit confusing. It should just be called latency. Whether it's a cache hit or cache miss, we need to spend that much time in the cache. Right? Remember, if there's a cache miss, we'll bring it back into the cache and then read it through the cache, right? So eventually it's going to be a cache hit. So hit time, we also need to suffer. But if there's a miss, right, I just mentioned we need that additional trip to the next memory hierarchy level. And depending on the miss rate, right, like how many misses do I have? And then I need to multiply that by the miss penalty. The question is, in question 2 of the assignment, we give you all of these numbers, but not miss penalty, right? What is miss penalty? Right, if there's a L1 cache miss, what is the penalty? Exactly, right? The time to access L2. And if there's a miss, I need to go all the way to memory. So we can recursively apply this formula, right? The miss penalty of L1 equals this part of L2. You just use all the numbers from L2, right? How many memory accesses do I have in L2? What is the hit time? What is the miss penalty? Well, actually, even ignore the percentage of memory instructions. Just this. This part of the formula is the average memory access time for any hierarchy level, right? So the miss penalty of L1, maybe I put it down over here, right? Forgive me if I'm taking, a few extra minutes of your time. So L1's miss penalty equals L2's average memory access time, right? And the average memory access time can be computed based on the L2's hit time plus L2's miss rate times miss penalty. For L2, the miss penalty is just the access time for DRAM, right? There's no way you can miss from the DRAM. Right. So recursively applying this formula and also adjusting it based on this split L1 cache, right? The memory CPI will be contributed by both instruction memory and data memory, right? So you'll have maybe an additional component to the formula. Again, this formula is not immediate proof. You need to understand the principle a little bit and then adapt it. All right, I have an example, but I think maybe I skip it, right? We can talk about it afterwards. And again, just bring back my favorite definition, or rather the way to prove that a miss is a conflict miss. I need to prove that it's, even with a fully associated cache with LRU policy, it is still a miss, then it is conflict miss. If we can solve the miss using a fully associative cache, then this is if we cannot solve the miss even with a fully associated cache, that means my cache is really not big enough, right? Then it's a capacity miss. All right, so that's all I have for today. Thank you everyone for joining me in person or online. And we can talk more afterwards. I'll leave my Zoom session on in case you have some questions you want to stay around. But right now I'll just walk through the room and take some in-person questions. All right, that's it. Yeah.
One little question. So I just want to confirm, I guess, my understanding of homework question 2.
Yep.
It's not, because there was a tricky question in class that was like, we're running a program that has 20% load store instructions. What is the average CPI or whatever? And you had to break it down to like, oh, we have 100% of the instructions that we still need to load, and then 20% times the rest. And that was because it's like the phrasing of we're running a program, right? Or
all right, I see your question. So it's actually a little bit related to this formula.
Yeah.
Right. So right now, well, you're saying the percentage of memory instruction will be 100% for each instruction I need to access instruction memory, plus the ratio of load store instructions, right? And that is correct, assuming that the instruction memory and the data memory have the same access time, right? Really, I have two components. I have percentage of instruction memory instructions, right? And then I have another component, right? Just continue with it, continue from the formula. Oh my God, how can I align them? And then percentage of D memory instructions, right? And then it's like, if we have separate L1 data cache and instruction cache, right? All of the numbers in this part will be the instruction L1 hit time, right? The instruction L1's miss rate, the instruction L1's miss penalty. And everything over here will be the data L1's hit time, data L1's miss rate, etc. Right? So if you have like two separate L1 caches, one for instruction, one for memory, then they must appear as two different parts in this formula because they will have different access time. But if we have a unified memory, or unified L1 cache, or instruction cache and data cache have the same latency, right, and same miss rate and everything is the same, then we can put them together as 100% plus 20% or 25%, whatever percentage load store instructions I have. Now, it's really because, in that case, these two numbers are the same. So I can apply, the distributivity law in math and then regroup the percentage ratio together.
So sorry, sorry, that lost me.
So if we have separate L1 and data cache, right, then we need, one computation for instruction cache, one computation for data cache.
That's two different CPIs, right?
Two different components of the CPI. They will be eventually accumulated.
But if we have a unified cache, you still need to fetch the instructions from memory and then the load store ones.
Yeah, for unified memory, you can apply the same formula. But the thing is, this part, this yellow box and this yellow box are equivalent. They're identical, right? If you have a unified memory. It's just like L1's hit time, right? Rather than two different kind of hit time numbers. If it's unified, these two components are the same. So you can do a regrouping by combining this number and this number. This is, what you have seen in lecture, 100% plus 20% multiplied by essentially the yellow box, right? You can do the separate computation.
I see.
Well, this is always correct.
Factor out the yellow box.
Yes.
And then there's a sum. I see. Okay.
Yes. Right. This like separate calculation for instruction and data is always correct.
Okay.
But if that number is the same, you may want to save yourself a bit of work but
I
just
see. If it's
factoring
unified
out.
cache, the penalty or all that.
All of those numbers are the same. Yes.
Okay. Thank you.
Yeah.
So when we see a question asking for the average CPI, do we always take into account of 100% memory instructions load time and also the 20%, 30% data memory?
Yes. What the most typically, right? We assume this is always 100%. Every instruction comes from the instruction memory. We need a place to save them, right? And they come from the memory. And this is number of data access instruction will be, the percentage of load plus the percentage of store.
Now, another question, going back to the conflict miss and capacity miss. I forgot which one was the answer for the slide you had.
Okay, so it's this point. All right, this is at the end of the first iteration. I have everything but A 0 to 15, right? That space is taken by B. And then the first access in the next iteration. Well, the table over there is already updated, so I'm gonna bring it back over to the previous slide, right? So the first time in the first access in the second iteration is A1, right? You agree with me? Bring to the front. Well, all right, it's already in the front. We're bring to the front. Right? This is the first access when I just change this to 1. Right? I equals 1, j equals 0, I'm accessing A1. Right? A1, well, we know it's a miss, it's not over here, and it is a capacity miss. And that's because, right, this cache is big enough to hold everything to hold everything in A. Right? It is big enough to hold everything in A. It's just big enough to hold everything in A. Right? So if I replace this with A 0 to 15, I have everything in A in the cache. Right? So it can hold 8 times 2, 16 blocks. Right? I only have 16 blocks in my array. But if one of them is taken by B, right now I have 17 blocks. Well, I use 17 blocks in the first iteration, and that is not big enough for the cache. Or sorry, that is too big for the cache. Right? The cache is not big enough. So in the first iteration, I accessed 17 blocks in total. Every block of A and also the first block in B. And even if this is fully associative, the first block in A is the one that I first accessed. So by the time I'm accessing the 17th block in the first iteration, including one B block, I'm going to throw away the oldest block, which is A 0 to 15, right? So even if the cache is fully associative, I'm maximizing my ability to remember the history, the block of A 0 to 15 is still going to be thrown away. So associativity doesn't help you addressing the cache miss. And therefore, the miss is because of associative as the size of the cache, right? The cache is too small. You need 17 blocks in the first iteration and to fully reuse them in the second iteration, but you only have 16 spaces in the cache. I know this definition is confusing. Right, conflict misses are misses that would not occur if cache were fully associative, right? So first I identify a miss, and then it's quite easy to distinguish whether it's compulsory or not, right? And if it's not compulsory, then I will just entirely rerun my program in a fully associated cache, right? Forget about the original cache. Assuming I have a fully associated cache of the same size with the LRU policy, same block size, and then can I solve that miss? If I can solve it, that means the cache is big enough to handle it, but it's because of conflict that causes the miss. If I still cannot solve it, that means if I cannot solve it with an associative cache, that means the cache is not big enough, right? So it's a capacity miss.
I mean, would conflict misses ever happen if we have a large enough cache?
Conflict zero.
Yes. Depends on the set size.
With fully associated.
With fully associated cache, you don't have conflict miss. You don't
if
have
it's big
you don't
enough,
have, you don't have it at all. Right.
Fully associated with the set is everything. So
You can't have conflict, right? If you don't have the data, it's because it's too old. You're already throwing it away, and it's too old because your cache is not big enough.
So under what circumstance will we have both conflict miss and capacity miss?
So if we have anything but the fully associated cache, we could have both types of misses. Right. So fully associative, we could only have capacity miss. Everything else we could have, either conflict or capacity, and we could of course always have compulsory in any placement. Yeah.
Back to the two equation for number two. So for a split cache, we would compute like the I cache stuff and then the D cache stuff, and then add everything together.
Yes.
Okay. So isn't it really very similar? Yes, between a unified and a split cache, because the only difference would be the same kind of penalty mistimes.
I forgot, what the question asks exactly. Like, what is the behavior difference between the instruction and data cache? If it's the same, then the average memory access time is going to be the same. Right.
So okay, here we're computing. I'm kind of breaking it down the instructions you need to get right with all the penalty stuff. With recursive stuff, right, as it goes down.
Yes.
And the kind of memory accesses program actually uses. And so there's always going to be those, free terms no matter what, right? Like
yes.
And stuff. And in this case, like rather than doing a percentage of everything, we're just going to do base CPI plus, I CPI.
Yeah.
Plus.
Yeah. Yes. We always have these components. Yeah. And by the way, this discussion section is officially over, but it's just like Q&A, right? And I do still have a participant online. Hey, Roman, do you have a question you want to speak up about? Yeah, bye.
No, I was wondering if you can explain the difference between fully associative cache and the set associative cache.
Okay. So the question is, the volume is very low. The difference between fully associated cache and set associated cache. Fully associated cache essentially has one big set of all the blocks, right? There's no order to these blocks, and oftentimes we just use this recently used policy, which means I'm keeping, all of the recent blocks. There won't be any conflict. And associative cache is just anything with like more than one set. Right, if we have 4 sets, we have 8 sets, but we also need to have multiple way associativity, right? Which means within each set there is more than one. There's more than one block, right? So, well, let me recap. If set size equals 1, block size is not 1, it's fully associative. If we have many sets but associativity is 1, like this, tall vertical bar, then this is direct map. Right, whenever you do indexing, you're just gonna find a block over there, and everything in between are like set associative cache.
Okay, thank you.
Mm-hmm. I know it's quite loaded.
So your office hours are noon, right on Zoom?
Yes, yes.
I think we'll be there.
Okay, yeah. All right, thank you. Yeah. And thank you everyone for your participation. I'm gonna stop the recording and then stop the meeting. I'm thinking